So we looked at two major approaches to the arrival time problem, or how to set up arrival times. And they have their pros and cons, right? So I mentioned that the absorptive arrival times, they allow very flexible modeling. So for example, you could have that in a finite dimensional system. You just write an absorbing term and then you see what happens, right? So also a harmonic oscillator, right? Whereas the covariant approach had this constraint on the spectrum of the Hamiltonian, had to be purely absolutely continuous, and you just don't always have it, right? So even like just a hydrogen atom or something like that would be problematic because you cannot describe the discrete spectrum. So so you're much more flexible. Also, you could say what it means to have the same absorbing term, the same detector term, in different potentials. So, for example, you look at a tunneling problem, and you could look at when the particles arrive with or without the tunnel, and you can ask this question and say, let's use the same detector, right? Whereas the detection, the covariant, in the covariant approach, what even is a detector depends on the dynamics, right? So if the covariance condition involves the dynamics, so you wouldn't know how to say that. So so definitely the absorptive approach is much more flexible. On the other hand, any two basically correct approaches to such a problem will have to have a big overlap. And so I'm now looking at the overlap, right? And also that this would mean that it tells you under what conditions you can turn this absorptive approach into the covariant approach. Actually, so absorptive times are by definition, right, after absorption is turned on. So we're looking at semigroups. Now, up to now, the implicit in the way we use semigroups, it's clear that this time at which this is turned on is time zero. So up to now, t is equal to 0, right? So this turned on to time when I turn on the device. But now let's think of a broader picture where actually maybe we have a free time evolution up until time zero, or maybe another time, up until zero, and after that we just apply the absorbing terms. So we can shift that, right? So shift turn on to another time. In order to not to get too much confused with the sign, let's say the time where we turn it on is t, but this is negative, right? And we'll later take t to minus infinity. Right? So if we do that, then we instead of our of the operator that describes arrival in the time interval m, this interval is actually taking at a later time, and this means that we have a c minus t star. Remember, t is negative, so this contraction semigroup is now used for a positive time, right? This is running for a positive time, and we take a ut here for the standard Heisenberg evolution, and so of course the stuff on the other side, right? So this is the same detection mechanism, but we apply it already at earlier times. So mostly this doesn't make much of a difference. So if we think of the detector sitting somewhere and we have free particles moving around, then at earlier times, typically the particle is far away, so it doesn't really matter whether we turn on the absorption or not, right? In an oscillator, it makes a huge difference. So this will actually be something that that makes the distinction between the spectra later on, right? So now if we let t go to infinity, we have this operator, to evaluate at large negative t, right? So so we define the wave operator. That's what they call it in scattering theory. Maybe W is a convenient. So this is the limit as t goes to minus infinity of this guy. Well, let's take the one without the stars. C minus t ut, right? And now there's no guarantee that this exists. It has something to do with that for times far away, the absorption process is negligible, right? So this then you can expect this to exist. So let us say, let us write the proviso here, if it exists in strong operator topology. Which is saying that if you apply this operator to a fixed vector, then you get a convergent sequence of vectors in the Hilbert space norm. So this is the wave operator, and now actually scattering theory does exactly that. So there you would have not a contractive, but just another time evolution, and and this maps. So if this exists, it tells you that asymptotically these move similarly, right? So the asymptote of maybe if you do Coulomb scattering, you compare the Coulomb Hamiltonian um, with a free Hamiltonian, and so for long times, if you don't look at the bound states, for long times the particles will move freely, and this wave operator makes the connection that maps you to the asymptote directly. So then, but here it has a very direct interpretation, right? We're just starting the detection process earlier. Also in the Hamiltonian case, that is, if you have two Hamiltonian evolutions, this doesn't always exist, right? There are conditions for this to exist, but they're sort of morally speaking, they're the same. They tell you that asymptotically they're similar, and the same could be asked here. So if we are in a good situation, then this actually makes sense. Now then, if it is so under that condition, so define, no, let's say f twiddle or something, right? F twiddle on any place in the time interval as the wave operator, which is like taking the limit of this guy, right? So actually, this is why I insist on strong topology, so that if this part converges and this part converges, the whole thing is going to converge. And so this is clearly still a positive operator, and now it's defined initially only for positive times, but you can see from this limit that if the limit exists, it doesn't matter whether I change the label a little bit. So I add a time s on that side and subtract it on that side. So we actually have always the property that W US is equal to C minus S W, right? For the times for which this is defined. So this is, you have an intertwining relation for such a limit between the two time evolutions. So the wave operator actually maps you from the free time evolution to the contractive one. That's inherent in this definition. So that also means that now obviously also the original F is a covariant observable with respect to the contractive evolution, right? So if you just shift everything to a later time, that is mapped by the contractive evolution. So this whole thing actually now becomes covariant, although only defined on the positive axis, but it becomes covariant for the free time evolution. So this is automatically covariant. And just to emphasize, right? So the F was was covariant with respect to the contractive evolution. But this is with respect to UT. Right? So it satisfies our condition of a covariant observable. So if there's, of course, it may not be normalized to everything because the absorption process might not catch every particle. So so it's subnormalized. But apart from that, it's exactly what I defined as a covariant time evolution. So scattering theory generally is considered as a perturbation theory of the absolutely continuous spectrum. So also for Hamiltonians, this doesn't converge if there's too much, or if there's any discrete spectrum, or only in trivial cases. So really, the scattering theory in general is something that you should think of as connecting asymptotic evolutions, and that is absolutely continuous spectrum. And so the condition that the covariant arrival times needs an absolutely continuous spectrum is actually implicit in the existence of this limit. For the oscillator, it just wouldn't exist, right? So you can't make this kind of turn on as early as you wish. It doesn't matter. It doesn't make sense. So when it makes sense, that is actually the case of an absolutely continuous spectrum. Then you do get the covariant arrival time out of an absorptive one. And so you could combine the best of both worlds, right? You could have like an arbitrary modeling, and you build this term, you build the contractive story, and then you compute the scattering theory, and you get a covariant arrival time that has a where you can say more precisely also what the joint measurements with arrival events are, and all these things that you can import from the absorptive side just by this simple transformation to map it to asymptotically ingoing free particles, undetected particles. So it's a bit tricky to find out when this scattering theory exists, but actually, so for the standard scattering theory of Hamiltonians, one of the nice and powerful general existence result is the Kuroda-Billman theorem, that says if the resolvent difference of two Hamiltonians is a trace class operator. So trace class perturbations are good for absolutely continuous spectrum. That we learned from Hermann Weil. So they are sort of sums of rank 1 perturbations. That's also how you prove it in some sense. So trace class perturbations are good in the purely Hamiltonian case, but if you go through the proofs, as far as I can see, I think this also just works for this contractive case. Now, a localized detector, like let's say potential, the M would be a multiplication operator that multiplies with something in a bounded region. Then the resolvent difference would easily be trace class. Right? So this is a typical thing. So you have free particle and localized detectors. They would tick this box, so you could expect the perturbation theory to exist. Computing it is another story, but I don't have the time to go into that. And there's also not terribly much you can say at full generality about this. So I stop here with also one more remark. We really had three approaches, right? So in the first I also described the detector models. That was the interactive arrival times, where you make an indirect measurement. Now, the scattering theory idea also works for that, right? So if you have an interacting situation and you're measuring on a probe, whatever you do there will be covariant with respect to the full evolution. But if the full evolution is asymptotically free and you have this kind of scattering theory, then you can do the same thing. You can convert it to something which is a covariant arrival time. Right? So even these detector models end up giving you covariant arrival times. And if you don't want to get into the details of the absorption process, and you just have your free evolution, This is a very convenient thing to have. So you have a compact description of the detector without actually describing how the thing gets absorbed in real time. So that's not so. So you don't have to follow the contractive dynamics. If you can do the scattering theory, you still have a good detector model that you can just apply at the level of the free time.